Okay, so we're talking about exponentials. By now, you should look at that problem and be able to say, oh, I know what the starting value is. What's the starting value? 2049. How about, is it growing or shrinking? Oh, I got some of you. See how I separated that into two parts? Sneaky, sneaky. It's actually growth. What growth is it? 49% growth. You can see it really easy when it's divided up like that. It's 49% growth. Here, see, if I had to put a 3, a lot of kids would have said that it was either 3% growth or 300% growth, and either way they would have been wrong. See, when I divide it up like this, I bet you'll be able to tell me what percent growth it is. 200% growth. That's why it's smart to write them that way. All right, this one, you could even write it as 1 minus 0.2, because that's what 0.8 is, and that would tell you it's 20% decay. But I bet a lot of you could just see that by looking at it, that it's 20% decay. All right? And this also got moved up. Don't forget that at the end. If that would take the whole graph, move the whole thing up. So let me make you think for a second. It's like, oh, starting value is 2049. Starting value is 80. Starting value is 2. No, it's not. Why isn't the starting value 2 this time? Because it would have been at 2, but then it got moved up 7. Another way to think of it is, the starting value is the y-intercept. The y-intercept is where, fill in this blank. The y-intercept is where, what? X equals 0. And if x equals 0, I put in a 0 here. This whole thing becomes 1. And then that turns into 1 times 2, which is just 2. But see how the answer is 2 plus 7? So the starting value here is not 2. It's what? It's 9. Okay, so you got to be careful on that kind. What the starting value is. Good trick question. All right, moving on. You see that the ones on the left are growth and the ones on the right are decay? All right, that's the main thing. And the other thing is that the tighter they are, the bigger the base is. Okay, if the base number gets bigger, it gets tighter and tighter until it's almost straight up and down with it's like 25 to the x. All right, moving on. There's the exponential one, and it's kind of sisters with the log one. And they are actually called somethings of each other. Inverses. So the point 3 comma 1 would be like the point 1 comma 3 on this one. They're inverses. They switch. They flip-flop. And they're flipping and flopping over this line right here, which is also known as the something function. Not integer. Identity. Identity function. All right. This is something you could calculate in your head if you knew how to break it up into 3 parts. Do you remember if you make it bigger first or smaller first? Make it smaller first, then make it bigger, and then the last thing you do is make it flip. Now 64 to the 1/3 is kind of nasty, but it's right on the edge of where some of you could probably do it. What do you think that is? 4. Good. Because that means 4 times 4 times 4 makes 64, right? So that's 4. So if that's 4, then I do what? Square it, and that makes 16, and then 1 over 16 is the final answer. Raise your hand if you followed me through that. You got that. Okay, good. Then you should be able to do this one. Everybody break that up into 3 parts, figure out the answer, and write it down. Make it smaller before you make it bigger. The last thing you do is you flip it. It actually could be done in any order. It's just that it'd be kind of stupid to do 4 to the 5th power. See, I could do it that way. And then figure out the square root of that. You see how that'd be kind of dumb? Because I got to figure out what 4 to the 5th is. I don't even know what it is. I get this massive number, then I got to take the square root of it, which I don't know what that is either because it'll be a massive number. Okay, but it would work because it's all multiplies, and with multiplication, any order is okay. But this is smarter because I can do that in my head. What's that part? 2, and then 2 to the 5th? 32, and then you do the negative thing, and it 1/32. Raise your hand if you had that one right on your paper. Good. Then here's a function. The one on the left, you should kind of know what that looks like. You should be able to say, I generally know it's exponential, and I generally know they kind of look like this. And if I wanted to know how steep it was, It's kind of between 2 and 3. You remember what E is? 2.7. Okay. So we know this thing is going up like this, fairly steep. How steep? That's a judgment call. I wouldn't mark you wrong for that. Okay, so now what do I do to make it turn into this? Well, there's 3 things. There's this and this and this. But the order you do them in makes a difference. Now, I know some teachers have taught it that you can go from the outside in, and that's true. I usually like to start on the inside and go out, because almost all math problems, if there's like nested parentheses and stuff, you always start on the inside. If there's functions of functions, you always start on the inside. So why not just keep consistent? Let's start on the inside. Do that first. Don't say it, write it. And then tell me what 2 and 3 would be. What order would you do it if I made you start on the inside? This is a typical test question. It's probably an R2 level, though. It's pretty easy. JR, how do you start? Correct. And in the front row.
Flip over the X.
Flip over X. That works. You could say reflect over X. You could say up, down, flip. And the last thing, down 5. Who had them in the right order? Raise your hand if you did. Good. We'll stop talking about that then. What if I tell you the starting point and one other point? That means that you could write this out, and then you could put the starting value here, and you could put the other point here, and you solve for B. All right, do it on this problem. You've learned this well enough. You should be able to handle this. Just like a test question. It's kind of on the easy side because the numbers are nice, but so if Mr. Van Dyke decides to put this in as the as a R2 level question, the numbers are probably like this. If he puts it in with like real world context, like a millionaire starts with $1 million and he invests it on, you know, the 14th of April. Then next year on the 14th of April he looks and it's up to $1.7 million. How much, or write the equation for it. Well, it's the same idea. He's giving you 2 points and you stick them in. All right, on this one, the 2 points I would use that for your start because you really have to, because the starting value is also known as the y-intercept, and the y-intercept is where x is 0. And so anyway, bottom line is that's a 4, so I put a 4 there. And then the other point, I would pick this one. You could pick a lot of different points, but some of them are easier than others. This one's nice because x is 1, and then I put a 1 here and an 8 there. B to the 1 is the same as b, right? So b must be 2. Do you get that? Have I answered the question, though? No, the question is to write the equation, and it's y equals 4 times 2 to the x. Raise your hand if you had that on your paper. Good, then you're doing it right. All right, let's jump right now to that harder kind where you'd have real world. In the year 2009, you have 125,000. Does that sound like a start? Okay, and then there's another point. But here's the tricky part. Doesn't it have to be 0?
No.
But I can make it 0. But if I make this a 0 to make it my start, then what does that have to be? A 1. Excellent. Now do the problem. Tell me the equation for Mr. Rich Guy. This isn't just rich guys that have 100 and some thousand in the bank. It should be you as you're getting older, because you need to have some money saved so that when you retire, you aren't like eating cat food. That's true. It'd probably a cat. You know, the neighbor leaves something out for his cat, and you're really hungry. You know, you do what you got to do. Okay. Y equals a b to the x. Y equals 125,000 b to the x. Now I stick in the numbers. I've got x is, if this is x and y, then x is 1 and y is 135,000. So I'm putting 135,000 here. And x is 1. 1 goes there. So then basically you just end up dividing 135,000 divided by 125,000 to solve this thing. And I think, cancel, B is equal to 1.08. Did anybody actually divide that and make sure I did that right? Good, thank you. All right, so if it's 1.08, what happened to rich guy's money? It increased. At what rate? 8%. So I could rewrite this equation for him and say, this is an exponential equation that models your investment portfolio. 125,000, and then the B would be 1.08 to the x. And it's exponential because there's an x in the exponent. Do you get that? 8% is pretty good, you're right. And if you could keep getting that over and over again, most people would just be very happy with that. Mr. Madoff, who was faking returns like this, would usually go about 9%. And that was believable, but yet not outrageously high. So people believed that they were getting 9%, and they were very happy with that return. In the end, he was just buying really expensive houses with their money. He wasn't actually investing it at all. And so it all came tumbling down at the end, of course. All right. Wait, I skipped over some stuff, and I want to go back to it. So this is all important. Here's another one. I don't even want to bother you with it because it's pretty simple. Do you see that there's a starting point and then another point? It's the same kind of a problem. It's just on a picture. All right. All right, this one. Describe the end behavior with limit notation. Do you remember how to write a limit? Let's see if you really do. Just write a limit for the way over there on the right side. How would you write the limit for way over here? You always start limits the same way. Limit of the function as x approaches, and then there's always an equal sign. That's how every single limit will ever always be written. Now you just got to fill in the blanks. X is infinity in this case because I said to go way over here. And y would be, well, when I got way over there, it would be infinitely high up there. Raise your hand if you had that one right. Good. Then the other one's super simple. You just change this to a negative infinity because it goes way to the left. And then what would it be then? 0. Good. That's using limits. Okay, here's one, except it looks a little different. Its limit, it looks like it limits out right here, and it does. This is a special kind of equation called a basic logistic function. And you know how I was showing you these two over and over, yeah, there, these three functions over and over again? Well, the basic logistic is one more of those big 12. Okay, so these are 3 of your big 12. We got another one of the big 12 today, and that is the basic logistic. And it looks like this. It's a kind of a cool function because it has a top. Most functions keep going up, 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 they go forever. This one is more realistic for populations. Populations limit out. They have a max. They top out. For instance, let's say that you had a lot of property in northern Minnesota and you put up a great big like 9-foot fence, which is supposed to be enough to keep deer from jumping out. You can do that. You can lock in your deer if you want to. Okay, so you've got this great big fence all the way around your property. Now they're protected unless you happen to box in some wolves with them. They're protected from people hunting them down unless they come over in a helicopter and shoot them, and that'd be pretty evil. Anyway, so you probably have these deer able to grow and grow and grow in population as long as there's a boy deer in there too. Anyway, kind of like that. Okay, so now this, it is. This is like, remember that was like an R4 kind of a question because you hadn't learned how to do it? Ta-da, you're learning how to do it now. Okay, so this, yeah, exactly. So this has a limit on it. Now, I don't know how many deer can live on an acre, but some smart naturalist guy probably could tell you that. But I can tell you that if you keep feeding them, that they would keep, the number of deer would just keep going up. But if you stopped feeding them, if you just like let them eat the natural habitat, then there's not that many deer could live on your property. There's definitely a limit, especially in the winter time. They run out of food really quick, and so they would be limited by that. So there would be this natural cycle that happens in the real world where if there's too many deer around, they start getting weak because they aren't getting enough food, and then the deer will hunt them down a lot easier, and it'll take down their not the deer, the wolves will hunt them down, and it'll be a lot easier to catch them. What we do nowadays is we aren't just leaning on the wolf population to keep them down. We actually issue hunting permits, and they judge by certain areas. There are some areas where they really have way too many deer, and so they offer these hunts. In fact, they have some areas that get really bad in the city, and they offer hunters the chance to come in for free and take as many deer as they can. So like these hunters don't go in with guns, because otherwise you'd be like seeing them walk down your street with shotguns. That'll be a little scary. They have them go in with bows and arrows, so it's completely silent, and they hide up in you know, like places that are fairly safe, like a little bit more remote, like some guy who's got like 3 acres or whatever, and they take as many deer as they can because they need to cut down the population. Because if they don't, the deer will eventually not have enough food, and they'll start dying, and that's even more sad, is to see all these deer that are, you know, wobbling around that can't get enough food. Anyway, so
Best job ever.
so some people get to hunt deer, and it's for their own good, except for the ones that you shoot. Anyway, this is a limit function, and here is, yes, that's okay, it's part of the learning process. Here is the official thing you need to write down for these functions. Write that down. I didn't put a star by this one because it's a new function, just as important as the exponential function. In fact, if you look close, it's got the exponential function in it. And this basic logistic function causes it to have a top. And the top, like right here, is a limit. And it also causes this function to be what's called bounded. It can't go any lower than 0. Think about it. Is your deer population going to go below 0? No. Negative deer are like zombie deer? That's an interesting concept. The limit goes there. Take a wild guess what the A is. Starting value. Start with 10 deer or whatever. This is this one's always a positive number in this kind of a function because we want it to grow. There's no such thing as a function that just decays. Okay, this kind of function goes up, and it goes up and up and up, but it has a limit on the top. And then whatever they put on the top number, if there's 5,000 deer maximum on your population, then you'd put a 5,000 there. All right. So this one is got an E in it. E is a number that's about 2.7, and this one also works for making these. You use these in different situations. All right, for today we're going to look at this kind, which has not got the E. It's got the starting value. And if this is my picture, can you see with your eyeballs the starting value?
Not very precise.
It's about 1.5. Okay, so then I'm going to go, wait a minute, L. L is on top. Maybe I should do that first. Can you see what the limit is? It might be hard to read. I'm going to read it for you. It's 5. Because it's going to get closer and closer to 5 but never touch it. So it's 5 over 1 plus the starting value, which was 1.5, times, now the growth rate. That one is something that we would give you. Okay, you would not have to be able to get that from this problem unless we didn't give it to you and you had to be smart enough to figure out how you could get it. Who is got a big brain and could figure out how we could figure out B? You could. Ah, yes, you could have another point. So if I had another point, like I see another point right there at 3, 4. And what could I do? Put it in there. I could put the 3 in here, and I could put the 4 in there, and I could figure out what B is. Be a pain in the butt, but you could do it. All right. Nope, that'd be like R. Yes, I suppose R3. It depends on how easy the numbers are. All right, so here's the kind of questions you're going to have to answer about this. You do not need to take notes on this right now because I'm going to do one with you just like this as the first problem of your homework. But I want you to pay attention while I show you. The domain here, the domain is how far it goes this way and how far it goes that way. So what do you think? Negative infinity to infinity. And the range is how low it goes to how high it goes. What would this be? 0 to 5. Would it actually touch 0 or 5? No. Continuous. Does this thing run along continuously, or is there holes along the way? It's continuous. There's no holes. There's no asymptotes. There's asymptotes that go this way, but they don't like block it. So this just flows continuously. There's no empty spots. Yes. Increasing or decreasing? What is it doing as you go from left to right? It's always increasing. All right. Symmetry. There is symmetry. We're not going to teach you how to do this. There is point symmetry, it's called. Like you could find a special spot on this line where if you do a double flip, you could. But we're not going to teach you that. So don't worry about symmetry. Next thing is boundedness. Boundedness is, how is this thing contained? Is it bound? You know, like somebody binds you. They have like tied your hands. You're like, you can't get out. Is this thing stuck between things? Yes, it is. It's bounded on the bottom with 0 and on the top with 5. So this is bounded. Yes. That's all you have to say. Extrema. Has it got local maximums and local minimums? No, it does not. Asymptotes. Yeah, I see a couple asymptotes. There's no verticals, but there are 2 horizontals, and they are at x. Oh, I did it wrong. Horizontals are y equals things. Sorry. Y equals 0 and y equals 5. And the last thing is end behavior, which you could describe with limits. If I said describe the end behavior, you'd say the limit of the function as x approaches infinity is 5. And the limit of the function as x approaches negative infinity, way over there, is 0. Okay, good enough. I think you get the idea on that. Here's our real world problem again. Here's another real world problem, and they've given us a function, and that's effectively telling us what the population's maximum is. Can you see it? 2,500, yes. It also told us that we started with 4 bunnies that are going to eventually turn into 2,500 bunnies. And because they're going to grow at what rate? 24%. I don't know how that happens. Maybe they divide. Anyways, y-intercept, the starting value, 4. The range of this thing, this graph is not the right graph for the bunnies, because that's from last. I just wanted to give an example of generally what they look like. But this would be 4 now, and its max would be at 2,500. Now it generally is looking right. Okay, so what's its range? 0 to, what's the highest it goes? 2,500. Okay, we don't want to do this all again. I think you get the idea. All right, we've come to the end. Now, this is the part where I do a problem with you out of the book. And I want to ask that you would go get your books. I'm going to pause for a second. If you want to borrow a book, leave me a shoe or a cell phone and grab one of those. Get it open to page 286. Okay, I'm unpausing the video because I wanted to show you one last thing before we start the homework. There is some stuff on this that you'll need to know. So I want to go over one more of these. I've changed the numbers a little bit. If you're looking at the 2 graphs, one's blue and one's red, can you tell which one's the 9 to the x? The blue one, because it's tighter. It's being stretched tighter. This is the blue one. Where is the blue one greater than or above the red one? Not from 1. 0 to infinity, because you're starting here, which is at 0. From 0 to infinity would be a correct answer. Or you could say when x is greater than 0. It's the same thing in this case. You get that? All right, that's one last topic I hadn't covered. All right, now, you're returning to page 286, number 45, and it's deceivingly, it looks really simple, but it's got like 8,000 parts. I will do this with you. We're only doing one of them. Question? Okay, a question on that. This thing. Yes, question. Well, it depends on the problem. I changed it from yesterday. Yesterday I had a less than there, but on this one, I have a greater than. If the question is, okay, let's pick a spot like right here. And I go up here, and you see how the red's here and the blue's there? Yep. The blue one is higher than and therefore bigger than the y value of it, yes. The x value at that moment would be exactly the same. All right, so moving back to here, number 45. Again, it looks simple, but it's got like 8 zillion parts. So Zach, would you read me the equation? Y equals...
3 times 2.
All right, and the first thing it says is to graph it. Now, I don't think you need a graphing calculator for this. We just need a sketch. And I think you should know enough on how to sketch this. You know it kind of looks like this, right? And then what's the starting value? This spot right here. So put a 3 there. And that's good enough. That's good enough graph. From there, we can do all this other stuff that they're going to ask us. We can look at that picture and answer the following questions. Mr. Z, could you read me the first thing they ask?
Domain.
Domain. Put a D on your paper. We'll understand that that means domain. The domain is, well, it's how far to the left, how far to the right. Negative infinity to... No, it'll go way to the right. Positive infinity. Domains are left-right things. Range is up-down stuff. How low will this one go? 0 to how far, how up will it go? Infinity. This kind of graph keeps going up. That other kind of graph limits out. This one doesn't. All right, domain, range. What's the next thing? Continuity. Does this thing stay continuous? It just keep going without any holes, without any hitches? Yes, it is continuous. Next question. Ink. Is this thing increasing or decreasing or both? It's only increasing. Next thing. Symmetry. Oh, you can skip that. Doesn't have any symmetry, but I'm not teaching you how to do point symmetry, so. Boundedness. Is this thing bound? No. It's got a lower boundary, but not an upper boundary. So why don't we say lower bound is 0. So it is kind of bound. It's sort of like in between. It's not completely bounded. It can keep going up forever, but it's got a lower boundary. What's the next one after boundedness? Extrema. Does this have any local minimums or local maximums? Nope. So I say none. I know it's got a, I mean, it's going to keep going up, but that's, even that, it doesn't even have a maximum. It keeps going up forever. Okay, after that, asymptotes. And this does have just one. 0. Y equals 0, very good. Because there's a dotted line right across there, it'll get closer and closer to and never touch. And the last thing is extra fun. End behavior, because the only way you can do that is describe it using limits. So it takes a lot of space, but they're really easy. Limit of the function as x approaches, well, that's how I always start anyway. And then I look at my picture, and I go way to the right end, and that would be x approaching infinity, sorry. And then I figure out what that is. And then you write the other one, and you say x approaches negative infinity, and that's the left end. You can handle finishing that yourself. Okay. The other kind of function, the next one on number 49, that one is one of these kind of functions, where after you sketch it, you'll kind of see that it's going limiting out. It's got a upper bound and a lower bound, and from there you'll have you'll know what the starting number is. Starting value goes right there. And once you got your picture kind of sketched, you'll be able to answer all these questions really easy. Okay? All right, I think I got your rolling on this one. If you need help, ask for help. I am going to be collecting homework scores in a minute.